Hello and welcome back to this course on computer organization. So having looked at the basics of digital systems that are needed to analyze a microprocessor for timing and other aspects, let us now get into building one. So here is the problem at hand. I want to add 16 numbers, 32-bit numbers, A0, which is 31 down to 0, to A1 of 31 down to 0, all the way till A15, 31 down to 0. Okay. So I want to perform the addition of these 32-bit numbers and get you the answer. Let's not worry about the overflow and all that, because when you add 16 numbers, you need 16 extra bits and all that. But let's assume that the numbers in each of these A0 to A15 is small enough such that the sum can also be contained in a 32-bit number. Okay. So therefore, eventually we want sum also to be 31:0. Okay. Now this can be done in a very obvious way by throwing in sufficient full adders, right, or sufficient ripple adders, 32-bit adders, multi-bit adders. Okay. So let us assume that I have this circle here is an adder, right, and I am going to feed these A0, A1, okay, and then I take the output of that guy, feed it to the next adder, so I'll get A2 here, right. So everything is a 32-bit number. Okay, you get A3, like this I go on all the way, and eventually I have to add A15 from here. The previous sum is going to come and I get the answer which is going to appear here, right. So it's how many adders do you need? You basically need for A0 and A1 you need one, and then you need one adder for every bit, every number after that. Okay. So therefore you have 15 minus 2, 13 plus 14 adders, 14, so you get 15 full adders, right. 15 32-bit adders, not full adders, 32-bit adders. Okay. And of course, we already know that, from if you do static timing analysis on that, the result of this adder depends on the arrival of the sum from the previous adder, which depends on the previous. So it basically, if you look at the critical path, it's going to go down like this, and that's going to be a very long path, and therefore you can optimize this whole addition operation a little more optimally by doing something like this, right. You do A0, A1, then you do A2 and A3 all the way down to A14, A15, right. So these are all adders. Then I put, so how many adders do I have in this stage? I have 8 adders because I have 16 by 2 of them. Likewise, I can put another bunch of adders here to add these two, right, and so on, right. You can do all this. So here you are going to have another 4 adders, then I'll have another 2 adders sitting like this, and finally 1 adder like this. Okay, and then you're going to get the sum here, which is also 31 down to 0. The only difference, so if you look at the number of adders here, it is 8 plus 4 plus 2 plus 1. This is also 15 adders, right? 15 32-bit adders. right? But the only thing is that the addition happens much faster and it is not going to take as long, okay. So there are essentially, the key point here is, if all the numbers that you have to add are available to you at t equal to 0, right, then there are many optimized implementations of this addition that you can do, like this. This is called an adder tree, by the way, right, and you can get the answer out in the fastest possible manner, okay. But now just think about, okay, this black box, okay, I'm going to talk about this black box here, which is going to just do the addition for you and give you the sum, right. So if you look at, all these are what you call the primary inputs, and this is your primary output of this block. So the primary inputs of that block are A1, A0 to A15, and each of these is a 32-bit number, right? Sorry, 31:0. So how many primary inputs do I have? This is equal to 16 times 32. Right, 2 power 5, 2 power 4, so you get 2 power 9, 512 inputs basically, right, 512 of them, and primary output is just sum of 31:0, which is a 32-bit output. Primary output is not an issue, but to assume that you can route 512 wires from various points into this block is simply impractical, and therefore it is not going to be possible to even use such a adder tree efficiently if you want to do something like this. In very rare occasions do you have access to all 512 numbers in which you can do this adder tree business and get away, right? So therefore you need a more intelligent way of doing this, okay. So let us now move on to a more efficient and practical way of doing this, which is basically the sequential addition. I want to do sequential addition, okay. So therefore now I have basically 16 numbers that, let's for the moment assume that I have somehow brought into my system, okay. We'll come to that a little later. Now once it comes into my system, I need to store it somewhere, and the storage element that we use, that we are already familiar with, is a register. A register is nothing but a bunch of flip-flops, okay. So therefore I am assuming in this case that I have 16 32-bit registers available to store these numbers for me, okay. R0, R1, right, R6, R15, right. Each of this is 32 bits, right. And then what do I want to do? I need an adder, right. So I am going to put my adder here. It turns out that I need just one adder because I am going to do this addition sequentially. So effectively what we are doing is this implementation, just that instead of having 15 separate adders, it's the same adder that we are going to use, get a partial product, add that to the next number and so on, right. So actually it is this way, but of course we know that that takes longer, and in fact now because it is sequential, it's being controlled by a clock, it will take some integer number of clock cycles. We'll see how many clock cycles and stuff like that, right. So I have an adder which is basically going to add numbers one by one from these registers. So therefore I need a way to first of all get these 16 register values, 32-bit values, to the full adder, right, and therefore that is going to be done through what is known as a data bus. So I have a data bus here, okay, which is basically 32-bit wire. It's a 32-bit wire that is just going to go, and what I am going to do is I am going to feed this through a multiplexer. Okay, the register values will come out like this. Okay, from R0 to R15, each of them being 32 bits, right? And I have a huge multiplexer, right, which is going to do this. So this basically means every bit from this, for example, register 0, 0 bit to register 15, 0 bit will get multiplexed in 116:1 multiplexer, and you will get the 0th bit from there. Likewise, first, second, third, all the way to number 31, right? So therefore, this is just a bunch of parallel multiplexers which are going to work, and I'll get an answer which is 32 bit, which I just connect to this data bus. Okay, how this is implemented we'll look at a little later. So now what do you do? I basically take this and give it to one input of the adder. Now what do I do to the other input of the adder? The other input of the adder, right, is, so for example, the second input, right, so this is what I am going to call the B bus, because it's the B input of the adder. What is the A input of the adder? This is the A bus. Okay, this is my A bus. Okay, this input, if I tie it to 0, right, what will happen when the multiplexer puts R0 value on the B bus, the adder will give R0 as the answer, R1 it will give R1. So that's not useful. Therefore, I need to find a way to feed the previous sum, the partial sum, back as the input to this A adder. Okay, and therefore I am going to call this the sum bus, right, and I am going to put a flip-flop here, bunch of flip-flops, again 32 flip-flops, right, that is a register and all that. And so what is going to happen? The sum will appear at the input of this flip-flop. When the clock ticks, data will go into the output, right, and that output is going to be fed back to this particular A bus, right. So this is, I am going to call this a clock. Okay. Now remember that my registers 0 to 15 need to be selected by a select line of the mux, right. How many select lines? It is 16:1 mux. Therefore, I need S3 to 0, select line 3 to 0, right. So since the operation that we are trying to do is very deterministic and fixed, that is simply adding numbers R0 to R15, I just need to sequentially go through all the registers. I don't need to go in any random order, right, and therefore I can basically put a counter here. I can put a counter here, okay, controlled by a clock, of course, right, which is simply going to make this guy count from 0, 0, 0, 0 to 1, 1, 1, 1, a 4-bit counter. Okay, this is therefore 4 bits. It will simply cycle through from 0 to 15 and then back. Okay, so all this is going to do is simply keep counting the 16 values again and again, and the answer will eventually appear. The partial sum will keep appearing in this, and eventually it will appear in the output of this register, which is we are going to call as answer. Okay, now there is only one problem here, the fact that initially what is the sum in this register? We don't know, right, and therefore just feeding this back blindly is not going to work. We need to do something interesting, where when we are actually trying to add register 0, it should be added to 0 in, I mean, when you are trying to add register 0 for the first time, this sum and answer should actually be 0 that goes into the adder, right. So for that reason, I am going to now put a multiplexer here, right, that is going to just select like this. This is 0, okay, this is reset, Okay, this is 0 and this is 1. So whenever reset goes high, you want 0 to appear at the full adder input. Now whenever reset is low, you want this to happen. You want the sum to feed back into this multiplexer so that the partial sum can now be added to the next register. So where does this reset signal come from? That also has to come from the counter, because all we need to do is look at is the count equal to all zeros. If it is all zeros, then generate this reset signal. So therefore, I will take this counter output and just pass it through a NAND gate, right? All zeros, right? Is it a NAND gate or no? It should be a NOR gate. It's a NOR gate, which basically is going to do NOR of the 4 counter bits. So when it is 0, 0, 0, 0, the NOR gate output will be 1 and reset will go high only at that point, right? This 4 bits out here, this NOR gate basically is actually, it's going to look like this: S0, S1, S2 and S3. These are the 4 select lines to the mux, and therefore you are going to get this, right? So effectively what we have done is we have used just one adder, a bunch of registers and one counter to build this compute system in a very efficient manner, right? So what we notice is there are two kinds of signal paths here. Okay, one is a data path and the other is a control path. So the control path is basically going to do, is going to control the flow of execution of this unit, right? That's going to decide how it is going to do the computations, what it is going to do. In this case, the control block is very simple. I will just draw it in red. It is this block here, right? You are just generating reset signal, you're generating the select signal for the registers in order to select which register. By the way, this collection of registers here is what we call a register file. A bunch of registers from which we can do some operations. What operations we will come to right now? These registers are purely allowing only read to be done. On the other hand, this register here, right, is allowing only write to be done. Okay, and read is happening by default because there is nothing else to select there and all that stuff. Read is of course happening. So your writing and reading is a hard-coded operation for that particular register out there, right? So in all, we have 16 registers sitting here and the 17th register which is sitting at this particular point in the that is taking the sum and giving the answer out actually, right? So it is also interesting to note that the rest of the signal path is basically just the data path. You know how data flows from to the ALU, to the compute unit, to doing some computation, whatever it is. Rest of it is just the data path. This red path is and control signals, right? Reset S3 to S0 are your control signals that are generated and are part of the control path, right? Now if I look at this black box here, right, remember we always need to worry about the black box that we are dealing with. Okay, so let me put that here or even further up, and if I look at this black box here, right, what is it? It is actually going to look like this. Right, so I'll explicitly bring this guy out, which is the clock. Okay, so this I can remove for now. So if you look at this black box, it has only one primary input, which is the clock. And if you want to get the answer out, this is my answer, which is 32 bits, right? And this is my answer, right? And of course, you need to know now at what point do you give the, get the answer and all that. So you need some indication to know at what point you have to sample the answer, right? So let's assume that that is also taken care from outside. So right now, if you look at the previous combinational blocks, we had 32 times 16, 512 inputs, 32-bit outputs. Now we are dealing with just one input and 32 outputs, right? So therefore, in that sense, this is still an efficient system and a very practical system, okay? So of course, in order to understand the working of this, you need to basically go through this sequential, diagram, state diagram and all that. So I'll just draw a couple of cycles, okay, clock, and this is my select line 3 down to 0, right? So let's assume that this is, okay. So I will not worry about the delays at this point. Right, so this is basically going to start with all zeros. 1, right? And this is my reset signal. What will happen? You will have reset going high like this and then staying low for 15 other cycles. Right? So for in the first clock cycle, when it is 0, you will have the select line going 0 and reset signal being generated because all of them are 0, right? And in the rest of the cycles, you will have reset signal going low. Okay, that means only in the first cycle will this 0 will appear on the A bus. Okay, so if you look at my A 15 0, right, this is just a combinational thing, right? So if you look at it, after some delay, it will show up the exact same value of that is at the input of the mux. So you will get 0 here, right? Then my A 31, right, and my B bus, which is B 31 down to 0, right. So this is going to select the multiplexer input is all zeros, so it will select the value of R0 onto this, right. In the next cycle, you will get R1, next cycle R2, R3 and so on. Now what will happen to my A bus? Remember, sum of 31:0. Okay, remember this is an important thing. So the sum is part of the combinational path, which is the output of the full adder. So the moment the A and B signals arrive correctly, after the full adder delays or the ripple adder delay or whatever that adder delay is, you will get the sum output to stabilize correctly. So now it will do R0 plus R1 and it will get you the answer like this. You will get R0. Okay. Now what is going to happen is at the next clock cycle, it is the answer that is going to be a delayed version of the sum by one clock cycle. So if you look at answer here, right, this cycle we do not know what the answer is, right, because some number has got generated and all that stuff, and this is some junk value. right? But the moment the next clock cycle, so this is clock cycle 1, 2. At clock cycle 2, whatever is in sum, right? This is my sum, I'm sorry, not S, right? Sum, whatever is in sum will appear here, and therefore you will get R0 here. And now that will go into A in the other cycles other than 0, all zeros. So you will get R0, and effectively you will add these signals, then the sum will become R0 plus R1, then in the next cycle you will get R0 plus R1, then you will get that coming back here, R0 plus R1, right? Then you will get R0 plus 1 plus 2, right? Then plus 3 and so on. So you wait, at the end of the 16th clock cycle, right? So at the end of the 16th clock cycle, you will basically get, in the 17th cycle, you will get the answer to store the full sum of R0 to R15, right? And of course, then the counter will reset back to 0, reset will go high, and then it will reset the A bus, right? But the answer at that point will still hold the partial sum of the previous round of addition that was actually done, right? So this way, what we have done is, we have taken a very hardware inefficient implementation from an area and resource perspective, made it a very efficient implementation, but at the expense of a larger computational time, right?